All right, purpose of today's video is to demonstrate how to work with exponential growth, but also how to provide evidence of your thinking during the process of working with exponential growth. So I'm less concerned about right or wrong answers here and more concerned about communication and quality of using mathematics and mathematics writing to say what you need to say. So in the first situation, we're given information about the world population. That in 1995 there were about 5.7 billion people, and there was an annual growth rate of 1.5% per year. So the first thing we observe is this is exponential growth. That's the assumption, and so we're going to use the exponential growth model and define my variables first, where x is years after 1995 and f of x represents billions. So that'll make me smaller, more manageable numbers. So in the beginning, I'm given information about 5.702 billion people, 0 years after 1995. That tells me that my a value in the model is my starting value, 5.702 billion. I also know there's a 1.5% growth rate. Now this is, if there's going to be any mistakes made, it's going to be on the conversion from the growth rate to the b value. The growth rate is 1.5%, but that means the growth factor is 101.5% because we're going to keep 100% of the world's population and an additional 1.5%. Converting that percentage to a decimal gives us our b value, which is also a growth factor in decimal form, 1.015. So be careful about where you put the zeros and the decimals, because a slight change on the left or right is going to have a dramatic impact on the world population. So I have my equation, f of x equals 5.702 times 1.015 to the x power. Now to answer the questions related to it, the first is what would be the population this year. And so I determined that this year happens to be 20 years after 1995, therefore x equals 20. And that gives us a population of 7.68 billion people by this year if the growth rate was correct. So now the actual population as of lunchtime today was 7.3 billion people, and so we were off by only about 300 million people. 300 million people is about the population of the United States, so we're off by an entire country's worth of people. However, given the fact that this was a 20-year projection, I would say that's surprisingly accurate results. Now, the challenge that I presented in class was, if the population actually is 7.3 billion instead of 7.68 billion, can we work backwards and figure out what the actual annual growth rate was over that 20-year span? It should be lower than 1.5%, but not by much. So the question is, how do we actually get this thing solved? To find out the actual growth rate. It's a challenge question. Who knows what the answer is? I know I don't, but I want to see what you guys do with that challenge. So good luck with that. Carrying on then, the last question was, when will the population be 10.5? Now we don't have a billion. We don't have the algebra to do this, but we can at least set up the algebraic equation. So this is the equation that I'm going to solve, and had I had the algebra, I would divide by the 5.702 and then find a way to get that x down to solve. But now I just use the graphing calculator, find the intersection, and I use that. So not only do I express the solution to the equation, not only do I express the equation itself and its solution, but I translate the solution into English and make sure that I answered the question. It says, in what year? And that was by the year 2036. The other thing that I need to do is to transfer whatever I saw on my calculator onto the page so that anybody reading will know what I saw when I looked at my calculator. You'll also see that I included the point representing the solution for the part B, which is the population this year. Alright, to continue then our journey, we're looking at the population of the United States now instead of the world versus the population of Indonesia. And 20 years ago, there were looks like about 65 million more people in the United States than there were in Indonesia. However, the growth rate of Indonesia is more than double the growth rate of the United States. And so it leads a question, like, when will the Indonesian population catch up to the United States population? And so we need functions for each. Oops, looks like my presentation started over. This would be the, again, I start off with the model, define my variables, Use an initial condition to determine my A value. Use the growth rate to determine the growth factor. Use the growth factor to determine the B value. And don't forget 2 zeros in between, so that shows a 0.7% annual growth rate. And that gives me my equation for the U.S. population. Similarly, with the Indonesian population, I use the same model and define the variables. And use the initial condition to determine the A value. Use the growth rate to convert to a growth factor, 100% plus an additional 1.6%, which gives me a B value of 1.016, just 1 0 in there. And now I have functions that I can use to answer related questions. For example, this year, 2015, is 20 years after 1990, so we can project, using f of 20, 302.6 million people in the United States this year. I didn't check that against the actual, but it's pretty decent. And in Indonesia, 272.53 million. Finally, the last question was asking, when will the Indonesian population be equal to the U.S. population? And the beauty of that is we can actually translate f of x is the U.S. population, g of x is the Indonesian population, so the question is, when will f of x equal g of x? So I've gone from English to an equation, and the equation can now be expressed in pure mathematical form, algebraic form. And because, again, we're not right there on the algebra yet, we are going to use the intersection in a graphing calculator, and I transfer what I saw in the graphing calculator onto my page, and I label everything so it can be used and interpreted. My solution is x equals 31.8, but I make sure I answer the question is, in the year 2026, the population of Indonesia and the United States will be the same. Notice again also in my graph, I also showed the answers to part C, and so we can kind of see how the trends are emerging. Another related question to exponential growth, and here we're going to assume exponential growth for everything we see. We're going to talk about populations usually, or investments, and in this case we're talking about a population of rats. So we had 10 rats in January and 15 rats in February, and from that we can establish a growth rate. And once we have the growth rate, we can project how many rats there will be by summer. Using the table as a way of displaying my information, I learned here that let me go back. That this month, or the first month, that would be t equals 0. I got that right here. January is t equals 0. There were 10 rats, and then February, that would be t equals 1, 15 rats. And so I use the initial condition to determine my A value, and I use the other given condition. 1 year later, we will have 15 rats, which gives me an equation. The equation is 10 times b equals 15. I solve for b and get b equals 1.5. Simple mathematics. It's algebra.